Hi, this is the Physics Chapter 12 Section 2 video, and this deals with sound intensity and resonance. Our objectives for this video are to calculate the intensity of sound waves, relate intensity, decibel level, and perceived loudness, and explain why resonance occurs. So those three things we're going to look at. First of all, sound intensity. As sound waves travel, they transfer energy from one particle to the next in the medium that they're traveling in. The rate at which that energy is traveled through a unit area of the plane is called the intensity of the wave. And since the rate of energy transfer, when we take energy divided by time, we have power, and so we can describe the intensity in terms of the power. And we use that, you see here this equation. Delta E means the change in energy, or the energy that flows through an area in a unit of time, and that is the power. Energy divided by time is power, and the area is 4 pi r squared, where r is the distance from the source. And so you'll see as we go into the next slide here that first of all, intensity has units of watts per square meter. If you remember, a watt is a joule per second. So what you're really saying is if you have an intensity of 1 watt per square meter, you have 1 joule passing through an area of a square meter in 1 second. The fact that the resistance, or the distance, the radius, is on the bottom and it's squared tells us that the intensity is inversely proportional to the square of the distance. So as you double your distance from the source, the intensity decreases by a factor of 4. It becomes 1/4 as much as it was before. And so that's an inverse square relation. And of course that happens because you're spreading the same amount of energy over a larger area, and that area is going to be proportional to the square of the distance. Here you see a graph, and this one is in your book, that shows the human hearing, the area of human hearing. A couple things to notice. First of all, both scales here are not linear, and you need to keep that in mind. You'll notice the distance from 20 to 50, a distance of 30, and now here from this square to this one, it's a smaller square, but we're going 50 units, and then from this square to that square is 1,000 units. And so this is a logarithmic scale, and this scale over here is logarithmic. Now this one, the intensity in watts per square meter, don't think that this 10 to the minus 12th watts per square meter is right around the threshold of hearing in the middle of the speech region, and so that's just a barely audible sound there. And you can see as we go up in intensity, we pass through the music region, the speech region, and eventually we get up here to the threshold of pain. Any sound above that threshold of pain can mean damage to your hearing. And so when your sound is, your music is on so loud that it hurts your ears, that's a sign that you need to turn it down. Okay, we can hear sound more easily in these middle frequencies than we can at the higher frequencies or at the lower frequencies. Now, the intensity of a sound wave determines its loudness, but it's not directly proportional to intensity. The perceived loudness is not directly proportional to intensity. Hearing in the human ear is logarithmic. In other words, twice the intensity does not mean twice the loudness, and so that causes some issues with doing calculations. We're not going to do that in our book now, so you don't have to worry about that. But relative intensity is the ratio of the intensity of a given sound wave to the intensity at the threshold of hearing. And because of the logarithmic dependence on perceived intensity or perceived loudness, using a number equal to 10 times the logarithm of the relative intensity is a good indicator for human perceptions of loudness. And this is where the idea of the decibel comes in. Okay, so decibels are used because we can look at those as being relatively similar to human hearing. So we use when we're measuring the loudness of sound, the perceived loudness of sound, we use the decibel scale. And here you can see some examples of that, and you see that a decibel level of 0 does not mean there's no noise. That means that is on the threshold of hearing. That's a sound that is just barely audible. And as we get into decibel levels higher than that, we have increasing loudness. Generally, a decibel level of 10 means it's twice as loud. Okay, that's a good approximation. So if the loudness goes up by 10 decibels, it's twice as loud. So going from 50 to 70 decibels, the 70 decibel noise would be 4 times as loud as the 50 decibel noise. Okay, let's kind of change gears here and look at resonance and forced vibrations. If you have a situation like this, you've got your rod here, a rigid rod, and you've got something connecting these pendulums. As you start one pendulum swinging, that is going to be transferred by this. This is a rubber band here. It's going to be transferred to the other pendulums, and they will start swinging. That swinging of those pendulums is called a forced vibration, and each pendulum has a natural frequency which is based on the length of the pendulum. So resonance occurs when the frequency of a force applied to a system matches the natural frequency. You can see in this, if this was the originally vibrating pendulum, this one would begin vibrating in resonance because it having the same length, it would have the same natural frequency as this one. They will vibrate a little bit, but it will not be as large as this one. This one will vibrate more largely because these will move around a little bit, but they won't really vibrate like this one, like these two do. Okay, these will have the one that resonates. This one here, if this was the original one swinging, this one will resonate. It will begin to vibrate back and forth almost as much as this one. These will not vibrate as much, and because their frequencies are different, their natural frequencies, they will tend to kind of dampen out.
Vibration of one object can cause another object nearby to vibrate as well. If the second object can vibrate at the same natural frequency as the first, large vibrations will occur in the second object. This phenomenon is an example of resonance. Resonance occurring between a vibrating tuning fork and a guitar string is greatest when the frequency of the sound wave produced by the tuning fork is the same as the fundamental frequency or lowest frequency of the guitar string.
Okay, now how exactly does the human ear hear? We have three sections in the human ear: the outer ear, the middle ear, and the inner ear. The outer ear consists of the fleshy part called the auricle, and that kind of works like a funnel that brings that funnels sound into the ear canal and brings it to the eardrum, which is the innermost part of what's considered the outer ear. The sound waves cause the eardrum to vibrate. That vibration is transferred by the three the three bones here. There's the hammer, the anvil, and the stirrup. Okay, those three bones transfer the sound to the cochlear window here, and it sets up vibrations in the cochlea. The cochlea is filled with a fluid, and this causes that fluid to vibrate. There are little hairs in the cochlea, and they are sensitive to different frequencies, and so as different ones are stimulated by the different frequencies, they pick that up and send that to the brain through the audio nerve, and your brain translates that then as sound.
Sound wave vibrations in the air pass through the auditory canal and cause the tympanic membrane, or eardrum, to vibrate. These vibrations are transmitted through the small bones of the middle ear to the oval window, a thin membrane which separates the middle ear from the inner ear. The inner ear contains the cochlea, a special sensory organ that converts the vibrations into nerve impulses. The cochlea is a long, coiled tube consisting of 3 fluid-filled chambers. The organ of Corti is found in the middle chamber. The membrane below it contains reed-like fibers. Differences in the physical characteristics of these fibers allow them to vibrate in response to different frequencies of sound. As a vibration pushes on the oval window, the fluid inside the cochlea is set in motion. The wave travels through the cochlea until it vibrates a fiber whose natural frequency matches its own. This motion causes the bending of very small hairs and the excitation of the nerve fibers at their base. Because only certain fibers vibrate, only certain nerve cells are excited. The nerve impulses travel along the auditory nerve until they reach the auditory centers in the brain, where they are interpreted as sound.